Welcome back to Fluid Mechanics. In this video, we will explore flow measurement. This topic is important in many real engineering applications such as pipelines, pumps, and water treatment systems. We will learn how engineers measure the speed and flow rate of fluids using different instruments. Objectives. By the end of this lesson, you should be able to explain the types of flow measuring equipment, calculate fluid flow using a Pitot tube, calculate flow rate using Orifice meters, Venturi meters, and Nozzle meters. What is flow measurement? Flow measurement means finding how much fluid passes through a pipe or channel over time. We can measure it as volume per second or mass per second. In industries, flow measurement is used to control process systems, detect leaks, and monitor efficiency. Types of flow meter. There are several types of flow meters: Pitot-Static Tube, Obstruction Flow Meter, Orifice Meter, Venturi Meter, Nozzle Meter. Other modern types such as turbine, ultrasonic, and laser-based flow meters. Each type has its own advantages, depending on accuracy, cost, and space available. Pitot-Static Tube. The Pitot-Static Tube is used to measure the local velocity of a fluid. It consists of a double tube connected to a pressure gauge. The device measures the difference between static pressure and stagnation pressure, and from that pressure difference, we can calculate the fluid speed. Advantages: simple and inexpensive, reliable with no moving parts, causes very small pressure drop, does not disturb the flow too much. However, it must be properly aligned with the flow to avoid error. This type of device works best for incompressible fluids and high-velocity flow. Obstruction flow meter. The obstruction flow meter is also called the differential pressure flow meter. It works by partially blocking the pipe so that the flow area becomes smaller. When the area decreases, the velocity increases and the pressure drops. By measuring the pressure difference before and after the obstruction, we can calculate the flow rate using Bernoulli's principle. Common obstruction meters are Orifice Meter, Venturi Meter, Nozzle Meter. Comparison of obstruction meters. Orifice Meter needs the least space, lowest cost, but least accurate. Venturi Meter needs the most space and cost, but gives the highest accuracy. Nozzle meter, in between the two, takes less space than a Venturi, but has more friction loss. Orifice meter. An orifice meter uses a thin, flat plate with a small circular hole in the center. It is very simple, cheap, and easy to install. However, it causes a larger pressure drop because of sharp edges and flow separation. Nozzle meter. In this meter, the flat plate is replaced with a smooth nozzle. The flow becomes more streamlined and energy losses are smaller than in the orifice meter. The nozzle meter is more expensive but gives better performance. Venturi meter. The Venturi meter is the most accurate flow meter. It has a smooth, converging, and diverging shape that minimizes friction and heat losses. Although expensive and larger in size, it gives very reliable results. Its discharge coefficient, which accounts for real losses, is usually between 0.95 and 0.99. All obstruction meters operate using Bernoulli's principle. When fluid moves faster through a smaller area, its pressure decreases. By measuring the pressure difference between 2 points, we can find the velocity and the volume flow rate. A correction factor called the discharge coefficient is applied to correct small energy losses due to friction. Example: Venturi meter. A Venturi meter is installed in a 6 cm diameter pipe with a 2.5 cm opening. The manometer shows a height difference of 5.3 cm of mercury. Using the discharge coefficient of 0.98, the flow rate can be calculated. From the result, we can find the average velocity of the fluid. This method shows how pressure measurement can be converted into actual flow rate. Example: Orifice Meter methanol flows through a 4 cm diameter pipe with a 3 cm orifice plate. The mercury manometer shows a height difference of 11 centimeters. We start with a guessed discharge coefficient value and calculate the flow rate. Then we find the Reynolds number and update the discharge coefficient using an experimental formula. We repeat this process until the guessed value and the calculated value are close enough. This process is called iteration, and it helps improve accuracy. Turbulent and transition flow. For accurate measurement, we must check whether the flow is laminar, transitional, or turbulent. We use the Reynolds number to determine this. If the Reynolds number is high, the flow is turbulent and the discharge coefficient value slightly changes. After calculating the final discharge coefficient, we can compute the exact flow rate and average velocity. Summary flow measurement is an important part of fluid mechanics. We can measure flow by using the Pitot tube or by creating pressure differences in devices like Orifice, Nozzle, and Venturi meters. Each method has different levels of accuracy, cost, and energy loss. Understanding these meters helps engineers design efficient fluid systems and ensure safe operation of pipelines and equipment.